So here are the list of the presentations that we have. As I mentioned, the title of this session is State of the Art of Numerical Head Modeling in tES, Methods and Applications. The handle is hashtag #any_webinar. You can use that if you want to post questions from Twitter. The talks are going to be in this order. First, Carla Sendra-Balcells will be talking about convolutional neural network segmentation for fast and robust optimization of the human brain. Then Jose Sanchez-Todo will be talking about a biologically realistic laminar neural mass modeling framework for tES, going down into the physiology part of things. Maria Chiara Biaggi will follow with a talk on targeting consciousness brain networks with TCS or tES in minimally conscious state patients. Ricardo Salvador will be talking about ActiSham, improving sham protocols in TCS with montage optimization. And finally, Laura Dubril-Weil will close with EEG biomarkers of TDCS neuromodulation of executive functions in healthy and ADHD populations, an example of applications of tES combined with EEG and ERPs. So without further ado, let me pass the mic and the video to Carla Sendra-Balcells for the first talk. And I remind you that if you have questions, please use the Q&A mechanism from Zoom, and we will make sure that we try to answer as many as possible. The talks are going to be about 10 to 15 minutes, and we have a cap of 20 minutes per talk. Okay, thank you very much. Carla.
Okay, thank you for the introduction, Julio. I'm going to share my screen now. Okay. Hope you can see it. Okay. Okay. So hello, everyone. I'm Carla from the Neuroelectrics research team. And now I'm going to talk about deep learning method that we designed for MRI segmentation in order to make it faster and more robust for a specific application, which is the human transcranial electrical current stimulation of the human brain. Okay, so here you can find a reference if you want to have a look to the preprint version of this paper. So first, I'm going to introduce you to the topic. Here we have the modeling pipeline we are using in neuroelectrics. First, we get the MRI data of the patient. Then we obtain the segmentation of the different head tissues. With this, we can create the 3D geometries. And in this model, we add all electrodes. Then we can calculate the electric field created by all possible pairs of electrodes. And finally, with this and with the target map, we can find the optimal montage using SteamWeaver, which is a software we are currently using in our company. Okay, but here we are gonna focus on the segmentation part, so we can obtain these different tissues: the scalp, the segmentation of the skull, the CSF, ventricles, and eyes, using several techniques, and we can obtain these segmentations in a few minutes. Sometimes we need to apply some manual corrections, but normally it's quite fast. And the problem is with the white matter and the gray matter segmentations, because as you can see, they have a really complex shape. And for our application, it's really important to get a good source-side definition. So for this reason, we use FreeSurfer, which is a standard tool used in research. But the problem is that it takes several hours. In a standard computer, you can spend 8 hours waiting for these segmentations, but it gives really good results because the segmentation technique is really focused on the surface. So the goals of this project were first, reduce the computation time of the white matter and the gray matter segmentations as compared to FreeSurfer, but preserving the accuracy. Second, work with just one input, a T1 weighted MRI, since in many applications the T2 is not available. And the third goal would be to create white matter and gray matter segmentations with a resolution that has proved to be enough to maintain a good source-side definition. In this case would be 0.5. And this is essential because in order to generate accurate electric field predictions. Okay, so here we have the methods. The first part was to generate or design a pre-processing pipeline, and this is a really important step because we want to make the neural network less dependent to data quality and acquisition. For this reason, we designed this pre-processing pipeline that is based on histogram matching in order to have all the data set with the same intensity distribution, more or less, and then image registration in order to have all the data set in the same space, in the same orientation, then cropping and other techniques. But these are the most important ones. And then, well, we built the architecture, which we named StarNet. This architecture is a convolutional neural network, which is based on an encoder and a decoder. The encoder is a ResNet architecture with 34 layers, so it's really deep and can capture lots of features. And we use transfer learning for the encoding part. So we use pre-trained weights. We used a ResNet architecture that was pre-trained before with a ImageNet dataset. And the decoder was using UNet skip connections in order to preserve features that might be lost during the encoding. And in this way, we preserve these features. In this case, the decoder was initialized with random weights. We also wanted to study a prior, which was slice identifier. So in this architecture, the input is the 2D input. So we are losing the third dimension. And in order to keep this third dimension, we decided to give to the last layers of the neural network information about the slice number. Yes, that's more or less. Then the third step would be the model training workflow. So here we have all the data set with the MRIs and segmentations, and we divide this data set in test and development. The test was kept apart and was not used during the model creation, just to check at the end the performance of the model. And finally, we have the development data set that is divided in validation and training. The training data set is given in different batches to the neural network. And for each iteration, we also gave to the neural network a batch of the validation dataset in order to get the validation metric, which is the dice coefficient, which is a metric that is commonly used for these cases for segmentation problems. And the training loss, if you want to know, it's across entropy. This process was repeated for several iterations, and Python was used, specifically PyTorch platform. Then we also wanted to test this neural network, not only with the dice coefficient, but also for real use cases. And these cases are, these applications are electrode montage optimization. So we built two different head models. The first one was using segmentations from white matter and gray matter segmentations from FreeSurfer. And the other head model was built using StarNet segmentations. And what we wanted to check is what we wanted to compare is the final optimal montage for both head models and see if they are similar or they have something in common. And then we also wanted to test this model with 18 MCS patients, minimally conscious state patients, because we saw that these patients have some lesions, some brain abnormalities, and FreeSurfer typically fails for these cases. Okay, so here we have the results. This is the dataset we've been using for our study. The IXI and ADNI dataset with FreeSurfer segmentations as ground truth were used for the training, validation, and test. We used 400 patients more or less for the training and validation, and 150 for the test. And dice coefficient average we got from the test was around 0.9. We also wanted to check the performance of the model using out-of-sample test data sets, using, of course, FreeSurfer segmentation as ground truth. And we got a similar result in terms of dice coefficient. So we can say that StarNet has a strong generalization ability. Then we also use 7 manual segmentations in order to compare the performance of FreeSurfer and StarNet by using as ground truth, in this case, manual segmentations. And we checked that using both methodologies tools, we got a really similar dice coefficient, which was 0.7. So StarNet gives comparable white matter and gray matter segmentations to free surfer. Here we have the plot of the training and validation loss that we can see that converged. And at the same time, the validation metric during the training, which is the dice coefficient, and we can see that keeps increasing during the training. And here we have some examples of white matter and gray matter segmentations for one MRI. We can see several slices, and in clear blue, we can see the false positives and false negatives. And some of them are highlighted in red, as you can see here. Most of them are in the boundaries, but in general, the results were quite nice. Okay, so here we have the results for the real use cases. First, we have the electrode montage optimization. So we built a head model using StarNet segmentations, and another one using free surfer segmentations, and using, of course, the same target map. What we saw is that the electrode montage was similar in terms of electrodes positions and also electric field and currents. Then we also, as I said before, we also test StarNet with 18 minimally conscious state patients. Here we can see some of them. We can see the segmentation of free surfer and StarNet. Here I'm just showing the ones that in which you can see a clear improvement. And we can see that while free surfer fails in some cases, in some patients, StarNet gives good results. Here we didn't have manual segmentations as ground truth in order to check the dice coefficient, but visually we can see that StarNet is more robust for these cases. Okay, so here we have the conclusions. First of all, StarNet, by using only one input, a T1 weighted MRI scan of any resolution, segments white matter and gray matter human brain tissues, reducing the computational time from hours to seconds. Second, StarNet proved to be a practical tool for tES, head modeling. And StarNet is especially valuable for segmentation in presence of gray matter or white matter large lesions. Here you have some references that I've been mentioning if you want to have a look. Thank you so much for listening. If you have any comment or idea, you can send me an email here. And you can also check out the poster in our social media. Thank you so much.
Thank you very much, Carla. So let's see. I don't see any questions in the Q&A panel right now. So if somebody wants to ask a question, please remember you can use this method. In the meantime, Carla, can you perhaps discuss a little bit what the next steps will be in the evolution of this approach? And also, how does it compare with recent work from the free surfer team, for instance, who is also interested in apparently doing work with deep learning for segmentation and processing of brain images? Okay.
So next steps, well, we've been working on a new architecture, so an improved architecture, in which is taking into account the neighbor slices. So instead of using just one input for the neural network, we are also giving the neighbor slices. So in order to take into account this third dimension that we are losing with 2D convolution, and it gave really nice results. And of course, apart from this, ideally, we would like to have a deep learning tool that not just segments the white matter and gray matter tissues, but segments all tissues at the same time. So just suggest the scalp, the ventricles. But this is a bit complicated or complex right now because we don't have enough data set. This convolutional neural network is really big and so needs a lot of data set for being trained. And in order to create this ground truth, we need a lot of human effort because we need to apply, as I said before, some manual corrections in some cases. So this is really time consuming. We have 100 patients right now, but it's not enough. So yeah, this could be an improvement for StarNet.
Thank you. One question that has come through the chat I hadn't seen from Chia Hua Chu. The question is about labeling. What labels do you actually use for the training? What are the ground truth labels?
So the class or the labels we are using is the white matter, the gray matter, and the background, which are all the rest of pixels.
Okay.
Yes, these three labels.
Thank you. I think that clarifies the question. Any other questions from our participants?
Where you were also mentioning which what FreeSurfer is doing right now,
Yes.
right? So I didn't answer this question, sorry. The thing is that now FreeSurfer recently has worked on a new approach that was using deep learning in their pipeline, but they use this deep learning technique in the first step. So in order to obtain the white matter segmentations and other tissues that we are not interested in. But then after this deep learning technique, they also apply post-processing, such as topology corrections or the creation of the gray matter surface, which takes, I don't know, five hours more or less, five hours and a half. So still it's a lot of time. I'm sure that their results are better in terms of source side definition, but for our application, deep learning technique is enough, as we've shown in this project.
Okay, thank you very much. So if there are no further questions, okay, thank you very much, Carla, again. Thank you. I know you have to run to class now, so we're going to continue with our next talk, which is going to be by José Sánchez Todo. She's going to be talking about a biologically realistic laminar neural mass model framework for tES research and optimization. So José, you have the floor.
Yes, thank you, Julio. I'll try to share my screen now. I hope you all hear me well.
Yep, we can hear and see the screen. Thank you.
Is it sharing? Okay, now.
Yep.
Perfect. So, okay, thank you, Carlo, by the way, for the presentation. It was really nice. So now it's my turn. I'm going to be talking about the biologically realistic laminar neural mass modeling framework for transcranial current stimulation. So in this presentation, I will be referring to transcranial electrical stimulation as tES for short. Okay. And okay, I would like to start with why we are doing this, basically. And in the field of transcranial electrical stimulation, there are mainly two challenges. One of them is to understand how it affects to the brain, which we still don't know. We have an idea, but we don't really understand it. And the other one is which parameters of this neuromodulatory technique we need to use in order to optimize brain function. And in order to address the challenges, what we've been doing is basically modeling the brain. And the traditional approach is what Carla has explained, which is to, wait, let's see if I can show my, here, which is to take the MRI of the patient, segment the different tissues, create a 3D geometry of each of the tissues, set some tissue conductivities in order to do the numerical calculation of the electric field, which is what you see here. And finally, use some optimization algorithms. I've got some reference here if you want to check, in order to target different areas of the brain. So this is a traditional way of doing this, and this is what we call biophysical brain model, basically, which we just take into account the geometry of each of the patients. But our vision in neuroelectrics is to expand this this modeling framework, and what we want is to add a physiological layer to this. So in not just taking into account the biophysics of the brain, but also the physiology of the brain. And combining these physiological models and biophysical brain models, we aim to create these hybrid brain models that can reproduce more accurate tES optimization for each of the patients. And in this talk or in this presentation, I'm just going to be focusing on this physiological brain model. So I'm going to start first by explaining what is a physiological brain model. So a physiological brain model is basically seeing the brain as a network where each of the nodes are different areas of the brain, and they are connected by we call the structural connectivity matrix, which comes from DTI or diffusion tensor imaging. And there are many ways to model the activity in each of these areas. I'm just going to discuss two here. So in order to model neural activity, what we can use is, for example, detailed compartment models where each of the nodes of this network represents a single neuron. And they're realistic, they're biologically plausible. So they are great to simulating single neuron recordings, but the problem is that if you want to model a whole area of the brain, they are really computationally expensive, and you cannot model the full brain with them, basically. So they are restricted to few columns. On the other hand, they're neuromass models, which they are more accurate in order to model the full brain because they represent an average population neural activity. So they can be compared with electrophysiological measurements such as EEG, for example. So they are better in this case. They are also not that computationally expensive. But the problem with them is that they don't represent the laminar physics or the physics of the gray matter, like the CSD, the local field potentials, or the current dipoles. So the objective of the study that I'm presenting here is, first of all, represent the laminar physics, such as the current source density, the current dipoles, or local field potentials. And the other objective that I'm going to be talking about is how to implement a tES model on this type of models. Okay, so to address the first objective, what we've done is to focus on real data. So we have based our modeling framework in this paper that I'm showing here, which is from Andre Bastos, where they recorded local field potentials from the prefrontal cortex of macaque monkeys while they were doing a working memory task. And I collect this figure of them because it shows the main results that they found, which are summarized here. First of all, what they found is that there's a slow oscillatory activity in deep layers, fast in superficial layers, and there's a drive from deep to superficial layers. The phase and the amplitude of the superficial oscillations are driven by the deep oscillatory activity of the column or the lamina. Okay, so these are the main findings, and these three are the ones that we want to have in our model, basically. So how did we implement that? This is our model. I'm not putting, okay, this is a note for everyone. I'm not putting here any equation of any model. This is the closer thing that you will have from the equations. So don't worry about the equations. If you have any questions or any doubts, just send an email to me and I will be happy to share. But due to time restrictions, I'm not able to explain all of them. But okay, so that's the note. So the neural mass model that I'm showing here, it's a combination of the Janssen-Reid neural mass model, which for the people that don't know what is it, it's representing an average population of pyramidal cells of the layer 5 in the cortex, that they are oscillating in alpha. And they are connected to slow inhibitory interneurons and excitatory interneurons as well, producing these slow oscillations here. We are also using a pyramidal interneuron gamma model oscillating in gamma, as the name says, which is a pyramidal population in layer 3 of the cortex connected to a fast inhibitory interneuron as well in the superficial layers. And also to simulate the drive from superficial to deep layers, what we have implemented in this model is a connection from deep to superficial pyramidal populations. Okay, so this is the neural mass model, and so far it has no physics at all. So I'm going to move forward and explain how from this we add some physical properties to it. So what we did is to take this column here, this simulated column here, and put it in a 3D space. So this is what you see here. This is just a simplification of the neural mass. Here you just see one of the pyramidal populations, the one that it's in layer 5, but we have two of them, as you saw in the previous slide. And in order to represent the physics, what we did is to set two different synapse locations in these pyramidal populations, because as you may know, the pyramidal populations are elongated. They have an elongated shape. So they have these apical dendrites and basal dendrites here. And we assume that when in each synapse, there's an inflow of ions coming in. So that creates like a current through all of the neural populations. So as ions come in, they have to come out if you assume that there's a current conservation. And here you see, or we have assumed that this is divided by 2 by this paper here, actually, just because in the soma we have a higher dendritic density, let's say. basically. So that's the idea. That's how we create the dipoles. We just have this cortical thickness, and we put two different locations for each of the synapses that the neural population is receiving. And this we do from the population in the layer 5 and the population in layer 3. So from this, we can calculate the electrostatic potential. Okay, so these are the synapse locations that I was referring to. So from here, we can calculate the electrostatic potential contribution for each of the monopoles in the model, and we assume them using the superposition principle, basically in order to extract this electrostatic potential here. And from this electrostatic potential, then we can derive other measurements, such as the normal component of the electric field and the current source density, which is what I'm showing here. And in these plots, actually, what you're seeing on the right is the power spectral density, and well, here you're just seeing that there's slow frequency oscillations in deep layers and fast in superficial layers, which is what actually we want to see. So this is our laminar neural mass model. I've also talked that our objective is to implement the transcranial electrical simulation model to it. So we have implemented what it's called the lambda E model, and this is a great reference for the ones that are interested on it. The lambda E model actually assumes that there's a membrane perturbation of the pyramidal population that depends on the orientation of the pyramidal population with respect to the electric field, basically. And we are just assuming that the pyramidal populations are affected by the stimulation just by their shape, as I have explained before. So yeah, that's the, I think I'm not doing anything, but that's the tES model that we're implementing here. All right, so let's see the results. These slides is really simple. I just want you to see or to compare the data that the paper was showing. This is the voltage distribution filtered in alpha and beta bands and filtered in gamma. And this is the output of our model. So here we can see the voltage here filtered in alpha and here filtered in gamma. But actually this can be better represented. Actually, we see at the relative power of per depth of these recordings. So here you see that there's a peak in the gamma frequency in the superficial layers and the peak in the slow activity in deep layers, and we actually could represent that as well in our model. This peak in superficial layers with gamma and in deep layers of alpha. Moreover, okay, so here what I'm representing is this drive that they were seeing from deep to superficial layers. Here you see the Granger causality, and you see that there's a deep modulation in alpha band towards the superficial layers in this band here. We were also able to simulate the results with our model. Moreover, there's the modulation index and phase. Well, there's a positive modulation index from deep alpha and beta phase towards the superficial gammas. We also were able to simulate that in our model, and some a really similar measure, which is the phase amplitude coupling, was also positive from deep slow to superficial fast oscillations. And finally, there's a negative amplitude coupling from the deep alpha and beta power towards the superficial gamma that we were also able to simulate in our model. So we can say that at least with these basic features that they were seeing in the laminar recordings, we still maintain them in the model that I've shown you. And finally, some results from the transcranial electrical stimulation model part. We don't have real data for that yet to validate the model or to compare with, but here we've done like a simple study where we have implemented an alternating current stimulation to our population, changing the frequency, which is the x-axis here, and the amplitude of the stimulation. And what you see actually is that the model, so here we have the deep layers, that the natural frequency of oscillating is alpha. So you see that the model resonates in this frequency as we increase the amplitude of the stimulation. And the same happens with the superficial neural mass that naturally oscillates in gamma band. And when we stimulate in this frequency and increase the power of oscillations, the neural mass model also resonates or increases the power of oscillation when we stimulate in this frequency. And that just shows that our model responds to an electrical simulation as well, or is it's able to, but we still need to validate this with real data and to perform some studies. So, okay, so to conclude, to conclude, I'm just going to read this. This laminar neural mass model framework provides a tool to develop fast specific models that match available in the in vivo primate data. And such models can also be generalized to reproduce activity of cortical columns under transcranial electrical stimulations in humans. And in this hybrid brain model formalism that I've been explaining in the introduction, which may be used to further develop optimization algorithms and dosing of transcranial electrical stimulation. And yeah, and that's all. Thank you very much for listening. If you have any questions, I will be happy to answer them.
Thank you very much, Jose. Thank you for that very nice presentation. Let me see, I don't see any questions at the moment. While people are thinking about it, I have a question that maybe you will want to, or a comment that you may want to further develop, which is about the importance of referencing when you do voltage measurements and the impact that this may have on your perception of what's going on, right? I mean, with when you look at the voltage plots, you seem to have this distribution of power in slow frequencies in the lower layers and high frequencies in the top layers, but this may not be that significant, right?
Right, yeah, that's a question that we are currently studying actually, because when we did this pilot study, that the one that I've just shown you, we didn't have the monkey data yet, but we have been analyzing now. And there's a lot of controversy with these measurements because people find some slow oscillations in deep layers and fast oscillations in superficial layers, but then you change the reference point and the distribution changes completely. So actually, if you reference, in this paper, actually they had the reference in the head pose of the monkey and they were seeing these results. But if you reference these results or you compute the CSD, you don't see the distribution of slow oscillations in deep layers and fast in superficial layers. So the distribution of frequency changes completely. And there's a lot of controversy, and we have read other literature about it. And yeah, we still need to study it further, but definitely the reference point where you are doing this type of studies is really important. And also maybe the voltage is not the best measurement that you should use in order to study the power distribution of the frequencies, but better to use CSD or to do this normal electric field measurement in order to study this distribution for sure.
Right, because the CSD and the normal electric field do not depend on the reference, right? That's an advantage. Yeah. So this leads me to the second question I had for you, which is you may want to comment a bit further on what is the advantage of using a laminar architecture for a neural mass model. I mean, we have already neural mass models like Janssen-Reed or Ping that have been used in the past. What is the advantage of going laminar? What is the added value of that?
Yeah, that's a good question. I mean, it's the relevance of this study actually. So the advantage in going laminar is that you can extract this. First of all, you can extract these physiological measurements, these physical measurements like the dipole or the local field potential or the CSD distribution. Actually, if you go laminar, and it makes it easier to compare it with real data to validate every model that you have. Also, it could contribute to, as a mechanistic model, to understand better some basic research on this question that you asked before, actually, where are these oscillations, actually, where are the generators of these oscillations? So these type of models can help to answer these questions. And finally, I think, as I said in the conclusions, these models can also help to develop better tES models, right? Because we have this physical measurement where we can interact with the electric field that we are trying to simulate. So they can be used to do what we think is the best to add this physiological layer into our transcranial electrical stimulation models.
Okay, thank you. And can you represent other models besides Janssen-Reed and Ping using this formalism? What is the
Yeah, definitely. That's a cool thing about these models, that you can use any type of neural mass model, any type of neural population. So if you want to implement I don't know, here it's just some type of interneurons, but you can develop complex models, more different type of oscillatory activity. So you have a huge range that you can explore of oscillations and different models in this. This is alpha and gamma, but you can use any other model that oscillates in any other frequencies. Very flexible.
Okay, thank you. Does anybody have any other questions? I don't see any other questions from the panel, so let me check Twitter. Nope. Okay, Rosé, well, thank you very much. Thanks for a very nice presentation.
Thank you.
Julio, I think there's a question in the
yes,
Q&A.
I missed one. Yeah. Okay, oh yes, you're right, actually. Thank you very much. Joseph Tharayil, sorry, is asking the following question. Could you give a bit more detail about the computational costs of the laminar model compared to traditional neuromass models? Is it computationally much more costly to run these models?
Well, it depends. If you compare it with the traditional Janssen-Reid neuromass model, yes, because we have more differential equations to solve, basically. But if you compare with other models that are also neural masses but are a bit more complex, they just take the same time to compute. So just to have the laminar or the physical measurements doesn't add any computational cost, actually, just the neural mass model per se. So it depends on the complexity of the neural mass model, I would say.
Right, there is an extra cost from computing the physical quantities, but it's not very great compared to the actual neural mass model itself.
Exactly.
Right. Okay, so, okay. All right, I think now there are no further questions. Okay, thank you again, Rosé.
Thank you very much.
Okay, so the next talk is by Maria Chiara Biaggi, who is going to be talking about targeting consciousness brain networks with tES in minimally conscious state patients. This is a especially interesting talk dealing with the challenges of modeling and optimizing brain stimulation in people in coma, basically, and with craniotomies and things like this. Thank you, Maria Chiara. Go ahead, please.
Yes, thank you, Julio, for the introduction. And in a second, I'm gonna share my screen. Yes. So I'm Maria Chiara Biaggi. And yes, in this talk, I'm going to show you an example of a practical application of computational head models in planning the tES intervention. And in particular, we're going to see how it's possible to target consciousness brain networks in minimally conscious state patients. So let's start with the definition of the problem. So minimally conscious state is a disorder of consciousness characterized by the fact that the patient partially retains conscious awareness. But to date, there is no definite treatment for this condition. However, it has been seen that tES can at least transiently improve signs of consciousness in this kind of patient. But the problem is that if we look at the literature, the results are often inconsistent, which means that not all the patients respond equally to the treatment. And one reason of this may be due to the fact that the montages used in these works are either derived heuristically or optimized on healthy patients that don't have any anatomical alteration in their head. Moreover, these montages are often applied in a one-size-fits-all approach, which means that the same montage is applied to all patients of the study. But here we argue that this may be not the optimal approach for this kind of patient, because in minimally conscious state, patients are often in the state as a result of traumatic brain injury. That means that they will have lesions often either in the brain or in the skull or in the scalp. And it's well known from computational head models that lesions affect the current distribution and therefore the electric field distribution on the cortex. So basically, when you go implementing a predefined montage on the subject, the effective stimulation may be different from the one you intended, and anyway is always suboptimal. So in this work, we used instead personalized biophysical head models to calculate personalized montages to address disorder of consciousness network. And we want to reply to this question, basically. Would personalized montages perform better than the standard applied so far in the literature? So in order to answer this question, we analyzed 9 subjects, out of which 4 had no significant lesion in their head, and 5 instead had a different kind of lesion also in combination. And we considered 3 networks associated with a disorder of consciousness that you have listed here. Then for each network, we identified a region of interest, a ROI, and these are for the executive network, it's the left dorsolateral prefrontal cortex that we set to excitation. For the external awareness network, we targeted 4 different patches in the left and right hemispheres of the in the frontoparietal areas, basically. And for the sleep network, we considered the whole network as a target. And as you can see then, all these targets have different extension, cortex coverage, and complexity. In particular, the first 2 are just the excitation areas, whereas, as I said, the sleep network has both areas set to excitation and to inhibition. Then the very first thing that we did was building up this head model. So here you have an example, for instance, for a healthy subject. So what we did is we started with a structural T1 MRI. We segmented the main tissue classes, and we assembled them into one head volume that you can see here. Then we placed small electrodes on predefined EEG positions on the skull. And we assign conductivities to the materials and the tissue of this volume. Finally, we meshed it with tetrahedral elements because we solved the equations for the electric field with a finite element method. So as I said, this is an example for a healthy subject in particular, but just for you to have an idea of the whole pool of candidates. So these are the 9 subjects that we analyzed. And I'm showing you here in particular this slide because you can appreciate how we represented the lesions. For instance, this was a scar in the skull out of a craniotomy that we represented here in black. In this case, we had, for instance, a craniectomy here and here. So basically, it was possible to take these lesions into account because they were visible in the MRI, in the T1, and they were finally represented as a region of different conductivity with respect to the healthy tissue. But now, so if we go back to our initial problems, once we had all the 9 head models, what we did was we mapped each of these ROI onto the specific cortex. And from that, we did basically 2 things. First of all, we calculated the electrical field distribution resulting from the standard montages that you have here. And here are the references for the montages. So basically, these are bipolar montages for the left dorsolateral prefrontal cortex. It's an 8 electrode channel with anode over each target area for the frontoparietal areas. And it's a 12 electrode montage optimized on a healthy subject for the sleep network. So once we had this normal electric field distribution, we calculated ERNI, which stands for error with respect to non-intervention. So ERNI is a measure of how well our electric field distribution fits the weighted target map. So it's a measure of the fitness of our montage to the target. And then what we did was we optimized for this ERNI value. This was possible using StimWeaver, which is an optimization algorithm we developed in the house in neuroelectrics. And basically, this optimization gives us montages that fit at best the weighted target electric field. And here you can see some example of our optimized montage for one subject, for this subject. So what we did here, one thing to keep in mind, actually 2 things to keep in mind are that we run optimization for focus, which means that we wanted to achieve the highest electric field possible in the target, while at the same time sparing a non-cortical target from an effect. And secondarily is that the amount of total injected current for the optimized personalized montage was set to be the same of the standard, obviously, for sake of comparison. So then we compared for each subject personalized and standard montages, and here are the results. So the very first thing that we did is we calculated these correlation matrices for the three targets. So here you have in the rows each subject of the study, and in the columns each personalized montage performances. So this value that we represent here is Ernie normalized, and basically what's important is that the closer to 1 this value is, the better it is the fitness of our montage solution to the target map. So the first column represents the standard montage, the diagonal represents the fitness of the personalized montages, and each column represents basically the performance of a montage optimized for one subject in each other subject. So from these matrices, we can already see that the value closer to 1 are the one on the diagonal. So the personalized montages already fit better the target map. But then we further analyzed these matrices. So first of all, we consider the average and standard deviation. And here they are. So we can already see that standard, well, personalized montage performs significantly better than the standard. So the improvement is significant. And also personalized montage have a lower standard deviation, which means that they fit equally well all the subjects. And from this average, we also see that cross montages, at least for left dorsolateral prefrontal cortex and frontoparietal area, also fit significantly better than the standard. This is not the case, however, for sleep. So this is believed to be an effect of a multi-channel solution, because we know that involving more channel basically maximizes the spatial resolution of the electric field. And in the very first two cases, in the very first two target map, we have that the personalized montages actually involve more channel than the standard, because here we had a bipolar solution versus a personalized montage involving 8 channel. And for frontoparietal, we had a standard involving 8 channel and a personalized montage involving 12. For the sleep network, instead, both standard and personalized montages involved 12 channel. So that's not the case. And also sleep network is the most complex one, which basically tells us that in order to have a really good fit, we really have to personalize the montage on that patient. We cannot use any other solution because that wouldn't fit well enough. Then we also stratify these results for the presence of lesion, because as I've told you at the beginning, often standard montages are derived from healthy subjects. So one may guess that in the pool of 9 subjects, those that didn't have any significant alteration in morphology would fit better the standard montages. But we see that here, that is actually not the case. We see that there is no significant difference in any target map in how well the standard montage fits subjects with or without lesion, which tells us that basically it's not enough. The presence of a lesion in one subject is not enough of an information to suggest the use of a personalized montage over a standard. One another thing that we did was evaluate this fitness in terms of area. So we evaluated the focality basically of the montages in terms of relative areas. So here we plotted the amount of target area that actually receives the intended stimulation. So that has a positive electric field, which means an excitation. And we see that for all the 3 target maps, this is significantly better for personalized montages with respect to the standard. And at the same time, if we plot the amount of non-cortical target area that experience high electric field, which means higher than a certain threshold, well, this amount is significantly lower for the personalized montages with respect to the standard. So basically, these tells us that personalized montages increase the target area subjected to the intended stimulation and spare more the non-target area. This is valid except for a bit of an increase in the sleep network, which means that basically personalized montages increase focality as we wanted to. Instead, in terms of intensity, we didn't observe any significant difference in the average electric field, neither on the target area nor on non-target area. But this is also to be expected because we, as I said at the beginning, we optimize for focus, not for intensity. So having a higher electric field on the target may be a byproduct of the optimization, but it's not to be taken for granted, especially because it exists a really well-known intensity focality trade-off that results basically from current limitation, for which you cannot really have both. You cannot have focality and intensity. And this is evident, or it's clear, if we look closer, let's say, at 3 subjects. So what we did here is we plotted the average electric field for the 3 target map in 3 random subjects. So we can see here, for instance, that personalized montages in pink may increase the average electric field on the target for one subject, for this subject, but they don't for another. Or for the same subject, for one target map, the personalized montage actually increases the electric field on that target area, but for one another target, it doesn't. So again, personalized montage may or may not increase the average electric field on target. This really much depends on the subject, where the lesion is and where the target is. But however, if we look at the focality in terms of area, this is always improved no matter what. So here you have the relative amount of target area experiencing excitation, and this is always higher, and the relative amount of area of non-target region that experience high electric field, this is always lower no matter what. And one last thing is that if we really care about optimizing for intensity, this is also possible. That's what we did here. So in this blue bar represent personalized montages optimized not for focus this time, but for intensity. So here we see that in these 3 subjects and in all the 3 target maps, these increase the average electric field on the target. But of course, this again is achieved at the expenses of, focality. As you can see here, then the percentage of non-cortical target that experience high electric field is always higher. So to sum it up, if we go back to our initial question, would personalized montage offering some sort of advantages with respect to the standard? We can answer that yes, they do, that they perform better both in terms of focality and fitness of the electric field distribution to the target map for all the target networks we considered here and independently of the presence of lesion. And we've seen also that it's possible to customize this personalized montage to optimize for intensity rather than focus. And again, they would perform better than the standard. And finally, the obvious step would be now to correlate this improvement in electric field distribution and targeting with behavioral or clinical improvement, trying this montage in real subjects. So with this, I conclude. I thank you for the attention. There is a poster in our website that goes over these results, and there is an article in preparation. You can send me an email to the address below, and here I'm trying to address some questions right now.
Thank you, Marichela. Thank you very much for that nice presentation. Let's see if we have any questions. I don't see any questions in the chat. I had a question or a comment that you may want to discuss a bit more. And it seems that, I mean, one of the conclusions from your work is that it's certainly beneficial to do personalized montages, especially in these patients. But one of the lessons from the study is that you only get out of the optimization what you optimize for, right? I mean, you cannot expect to optimize all kinds of features. If you are focusing, for instance, if you're interested in focality, then you may, there's a trade-off with intensity and so on. Can you discuss a little bit that and how you manage to work with those trade-offs by using a weight map and a target map at the same time?
Yeah. Well, the key to leverage on both of these, to leverage on focality versus intensity trade-off, we have various ways. First of all, the trade-off is a consequence of current limitation and also on a number of electrodes limitation. So one first thing that we could do basically is just to release some of this constraint, especially, well, they will act non-linearly, so it really depends on the interplay of the three of them. But releasing, for instance, total maximum current would make more energy available to be injected in the brain. So it could be that these would affect positively the intensity. The trade-off will be still there, but everything will be scaled up. And then of course, this is one way. When it's not possible because current constraints are set basically by safety limitation, and also, for instance, number of electrodes is more a technological constraint. So this may not be possible to play with the constraint. One other thing we could do is leverage on the weight map. So basically on the relative importance of the target area with each other. So for instance, in the focus optimization, this is achieved by setting a lower weight for the cortical area to spare. So we want to impose that the cortical area do not have to be, there must be no electric field with a certain weight, with a certain importance. Well, we can really much decrease that importance to 0 to release the constraint for focality, and therefore basically just have intensity optimization.
Okay, thank you. Another question that I had written down here is, what type of data do you need to do this optimization and this analysis? What type of MRI data are you using or other to build these models?
Yeah, to build up the ad model.
Best of worlds.
For the ad models here, we had to make do with T1 weighted MRI images. The resolution was adequate because we needed at least 1 millimeter resolution in the 3 directions. But this was just a T1 contrast. Obviously, the more information we get from MRI, from structural images, the better it is. So for instance, we could use fat suppression for MRI, first of all. This would give us better contrast for the skin when we have to segment. And we could use also T2 weighted images that would give us a better detail of how the skull is, and possibly also differentiate between the different types of skull.
Okay, we have another question from Benjamin Calop, and it's like this: what do you think about optimization of the local E-field orientation? I am referring here to the notion that E-field orthogonal to the cortical sheath is better. Are you actually controlling for that in your optimization?
Oh yeah, I mean, I took this for granted because it was, for time constraint, but we are optimizing for a normal electric field, which means it's always orthogonal to the cortex orientation. It's possible, I know we don't currently we didn't implement it yet, but it's possible also to control the orientation, like not just tangential or normal, but there are algorithms that control exactly the angle, or at least a variation of the angle.
But in our method, we are focusing on the normal component of the electric field, right?
Yeah, because we assume that it's what we're having actually an action on pyramidal neuron. These are the vast majority of neuron in the cortex, and these are oriented perpendicularly. So the electric field, to have enough of an action, must be aligned with the axon, and that's why we use normal electric field orientation. I mean, it has a physiological.
Yes, this was discussed in the previous presentation by Rosa Sanchez Todo as well. Okay, any other questions from the panelists or from the public? Okay, then if not, thank you very much, Maria Chiara, again for your nice presentation. And we're gonna move now to our next panelist, Ricardo Salvador, who is going to be talking about improving sham protocols in tES with montage optimization. And this is the ActiSham, the term that is going to be explained here. It's a new way to handle placebo sham in tES. So you have the floor. Let's see, just perfect.
Okay, thank you, Julio. And welcome to this presentation. Okay. So in the last presentation by my colleague Maria Chiara, we saw how montage optimization and computational head models can be used to optimize stimulation parameters, optimize dose parameters, to focus more precisely on stimulation on a specific cortical region of interest. Here we'll see another application of computational head models and these montage optimization algorithms, this time to improve on sham protocols. And we have a new method that we're proposing to do sham that we believe has some advantages over conventional methods. So what's the problem with conventional sham methods in tES, transcranial electrical stimulation? So usually transcranial electrical stimulation, sham is applied with the PHYSPHO protocol. So at the beginning of stimulation, there's a very short ramp up of the current. Then the current reaches a plateau for a few seconds, and then it ramps down and it remains down throughout most of the stimulation duration. And sometimes in other protocols, there's another period like this one at the end of stimulation. This is effective in the way that during most of stimulation, there's no electric field induced in the head, and therefore there's no effects of stimulation. However, the problem is that patients can actually tell the difference. If we look at this paper that was published in 2018, the authors of this paper, they compared two different montages. So they compared one montage in two conditions, sham and active stimulation. The montage was a very simple bipolar montage with one anode over F3 and another anode over the contralateral eyebrow. And then after the end of stimulation, they asked the participants if they thought they had received active or sham stimulation. And what they recorded was that most patients that had received sham stimulation replied that they thought they had received sham stimulation, whereas most patients that had received real stimulation thought that they had received real stimulation. So as you can see in this study, this way of doing sham wasn't fooling the participants or blinding the participants well enough. And they also asked the participants to quantify their sensory feedback, so the sensations they felt, the tingling sensation, for instance, under the electrodes. And the participants that had been intervened with sham stimulation reported lower sensations or weaker sensations than the ones that had received real stimulation. So the question here is, and the objective of this work is, can we develop a sham approach that, on one hand, blinds the subjects more efficiently to what form of stimulation is being performed on them as compared to conventional methods for sham, and of course, still doesn't have an effect on the subject. And in order to do this, we'll leverage the same type of computational head models that my colleague Maria Chiara mentioned in the previous presentation. So I'm going to briefly describe the process of generating these head models again, even though you already seen this a couple of times. I think it's important to receive the same information many times in order for it to sink in. These methods, they often have, they often employ different algorithms, but they often have the same steps. So the models, like you've seen, are created usually from T1, at least from a T1 MRI. MRIs are usually employed because they have good spatial resolution, they have good contrast for the tissues that we're interested in, the head, and they use non-ionizing radiation. The images are then segmented into different tissue types, and then a 3D representation of each tissue is created. And at this stage, you can also add to your scalp representations of the electrodes that you'll use in your work. Here, we're interested in multi-channel approaches. So we modeled very small electrodes, 1 centimeter radius electrodes, high-steam electrodes that Neuroelectrics commercializes. Of course, that then you have to calculate. You can calculate the electric field distribution with any montage of electrodes. And to do this, we usually use numerical methods like the finite element method. And then you need to, if you want to use these head models for montage optimization algorithms, you need a way to generate the electric field with any combination of these electrodes really fast. So you need to calculate something we call the lead field matrix, which is basically the information about the electric field in every point of the cortical surface, induced by every bipolar configuration of electrodes with one common cathode. And in this case, we used CZ as a common cathode. And due to the linearity principle, any combination, or if you want to know the electric field distribution with any combination of electrodes, you just have to multiply that lead field matrix by the vector that has all the currents in the electrodes. Now, how can we use this to optimize a montage? So here I'll focus on the Steamweaver algorithm, which is an algorithm that my colleagues mentioned in the past. The Steamweaver algorithm is described in this paper by Ruffini and al. In 2014. But the objective function of this method is to minimize the least square difference between a weighted target electric field and the weighted electric field induced by the montage that you are testing, evaluating. And we call this difference ERNI. And how do we define this weight and target electric field? So the weight is just a map of how important a specific node on the cortical surface is to the optimization. It's just a scalar between 1 and 10. We usually just set a really high value for the region that we want to stimulate and a low value for the regions that we're not interested in stimulating. Regarding the target electric field, this is a bit more complex because as you know, the electric field is a vector. So you need to specify not only the magnitude of the electric field, but also the direction of the electric field. So the natural question here is, what direction of the electric field do you focus on? Now, in this work in particular, we focused on the component of the electric field normal to the cortical surface. And why did we focus on this surface? Well, on this component of the electric field, we focused on this component because we think that the cells in the cortex that are more susceptible to the effects of stimulation are pyramidal cells in the cortex. And these cells, they tend to be aligned mostly perpendicularly to the cortical surface. So according to a simple model of interaction, the component of the electric field that is more likely to influence the polarization of the soma of these cells is the normal component of the electric field. And in our convention, if the electric field points into the cortical surface, and that leads to a depolarization of the soma of the pyramidal cells, and therefore that will lead to an increase in cortical excitability. If the electric field has the opposite orientation, then we have the opposite effect. So in this component, like I said, we'll focus on the normal component of the electric field, and we'll set the value of 0.25 volts per meter for the target electric field, because this is a reasonable value that you can achieve in stimulation with the usual constraints, current constraints that you have available. So this picture here shows the head model that we used in this study. In the picture in the middle, you see the target region highlighted in red. This is Brodmann area 46, and it corresponds roughly to the left dorsolateral prefrontal cortex, which is a common target in many tES applications. And on the figure on the right, you see the optimized montage and the distribution of the normal component of the electric field on the cortical surface. So positive values here indicate that the electric field is going into the cortical surface, therefore leading to an increase in cortical excitability, whereas negative values, they have the opposite interpretation. We limited this solution to a maximum of 2 milliamps per channel and a maximum the total injected current of 4 milliamps. And we limited the number of electrodes in the simulation to 8, but we could have chosen different values. Now, how can we use this to implement a better version of sham in stimulation? So let's imagine that we'll get all the currents in all the electrodes in the optimized montage, and we'll put them in a vector X. One naive way of using these methods to come up with a montage that achieves sham is simply to run the same orientation, the same optimization, but now with a very low value for the particle electric field, let's say 0.001 volts per meter, a value very close to 0. What's the problem with this approach? The problem with this approach is that if we just run it like this, the optimizer will give us the trivial solution. So it will set all the currents in all the electrodes to 0, which isn't a very efficient way to do sham. So we need to impose another constraint, and in this work, we propose to use the following constraint. We constrain the currents in at least one of the electrodes in the stimulation to have a specific value, let's say 500 microamps. 500 microamps, according to our internal testing, shows that this is the value that elicits a sensory feedback in most participants. Of course, that it can be more or it can be less. Another point in this is that even if you achieve a montage that has a very low electric field and has currents that aren't 0, probably the optimizer will still pick electrodes that are far away from the area of interest. And again, this wouldn't be a very efficient way of blinding the participant, because in that case, the sensory feedback might be different. So in addition to this, we'll also demand that the optimizer uses just the pool of electrodes that was picked up by the active montage. And the question now is, which electrode do we select that has this fixed current of 500 microamps? So we have to run different optimizations, in this case, 8 optimizations. For each optimization, we come up with a montage. And at the end, the question is, which montage do we choose? And in this work, we chose the montage that minimizes the average electric field on target. We could have chosen another criteria. We went for this one in this work. And in this case, it was the electrode that's selected as the ECHI electrode AF3. So this figure here compares the distribution of the normal component of the electric field in the active montage on the left and in the active sham montage on the right. As you can see, the electric field induced in the active sham montage is much lower than the electric field induced in the active montage, but the currents aren't exactly negligible. There are significant currents being used by the active sham montage. So the natural question is, how does this work? Since we're injecting currents into the brain, but these currents aren't resulting in any significant electric fields, why is that? Well, if we look at the distribution of the electrodes, we'll see that the optimizer did something very clever here, which was to maximize current shunting between the electrodes. What is current shunting? Current shunting is a normal physical phenomena that occurs in tES, in which if you have an anode and a cathode located close by, some of the current that you inject in the anode won't go to the brain, but it will be shunted through the scalp towards the cathode. And this, of course, is increased if you have the anode and the cathode located close by. And what the active sham montage does is that it chooses a very clever interleaved distribution of the anodes and the cathodes in the montage that maximizes this current shunting through the skin. So what's happening is that most of the current that you inject in the electrodes in the active sham montage is shunted through the skin and doesn't generate any substantial electric field on target. So to conclude, the active sham approach employs numerical head models and montage optimization algorithms to achieve subject-specific montages that can be used to implement sham protocols. Again, I stress that this is a subject-specific approach, so this requires that specific head models be created for each of the subjects, for each of the participants of the study. And the electric field induced in the active montage is much, much higher than the electric field induced in the sham montage. In this particular case that we've shown here, the ratio between the electric field in the active and the sham montage is 260 times. And this ratio is much higher than the ratio of the currents. So this difference in electric field isn't just explained by a decrease in the currents. This is also explained by the clever positioning of the electrode that will increase current shunting through the skin. And the fact that the active sham montage also employs the same set of the electrodes as the active solution makes this approach very easy to be implemented in double-blind protocols. So protocols in that neither the subject or the operator know which type of montage is being applied. We published in 2019 a paper that has that explains also this approach in conjunction with a different target. In this paper, we use the target in the left motor cortex. So if you want to know more details about this approach, I encourage you to read this paper. And this concludes my presentation. So if you have any comments or questions, I'll be answering them now.
Okay, you have a question here from Marco Mikkonen. I don't know if you can see it, but I will read it. There is a large amount of uncertainty in conductivity values of biological tissues. How does the conductivity of the skin use affect active sham?
Yes, this is a very good question. Thank you. Well, like you mentioned correctly, there is a great uncertainty in the conductivity values. This also affects the skin, and it varies substantially from subject to subject, and it also depends on the subject's age. However, regarding the shunting through the skin, the most important parameter is that the conductivity of the skin is much higher than the conductivity of the scalp underneath. And this is always the case. I mean, even though there is variation in the values, there will be always a much higher conductivity in the skin than in the scalp. So this approach will always work. Of course, that if we use standard values, we might be slightly overestimating or underestimating the electric field that's induced in the gray matter. But this is the current limitation of all computational head models today, unfortunately. And this can only be answered with the new approaches that are being used to measure the conductivities in vivo. And I believe that in the next few years, we'll have ways of doing this in a practical manner. So in a way that's fast and that can be implemented in every study.
Yes, thank you, Ricardo. I would also, I mean, that's definitely a good question. I think experiments need to be run also to validate the technique. We have already 2 examples, one from Dagan et al. In 2018, and the recent one by Neri et al. Showing that at least in this works, in this research, the technique was successfully at blinding people and successful in the sense of not producing physiological effects like the active condition was. So that's one positive aspect. Let's see, we have another question here by Setare Rezadkani. Thank you for your presentation. Can I ask the name of software you use to produce this 3D segmented model? Is it FreeSurfer?
In this particular model, we used FreeSurfer to segment the gray matter and the white matter. And we used SPM 8 with the Mars toolbox to segment for the other tissues, so the scalp, the skull, and the CSF. However, we use different methods depending on the data set that we have available. Right now, I can tell you that we're using SimNIPS for most of our work, except when the models have lesions, and for that, we use the same type of approaches that my colleague Carla was mentioning in the first presentation.
Thank you. I have another question that you may want to comment on, and that is, you showed a very nice result here in the sense that you had a 250 change between the active and the sham condition in terms of the average electric field on target. How general is that, and how does it depend on the type of target that you have to deal with, if it's very localized or if it's a spread target? How robust is the method with regards to the optimization problem that you want to solve?
Yes, that's a very good question, and we can't expect always to have such a high ratio between the active and the active sham montage. This depends not only on the target size, but it also depends on the available electrode positions that we have. So since this current shunting favors or happens more strongly in montages that have the electrodes close by, if you have a more sparse array of available positions, this sham through the scalp won't be as strong, and you can't expect such a reduction. So in order to maximize the effect of shunting, you should use a denser array of electrodes. And I mean, thankfully, the direction of the technology seems to be that one, seems to be of employing denser and denser arrays of stimulating electrodes as we progress. Regarding the effects of area size, it's a little bit harder to generalize. What we can expect is that if the target is very localized, just 1 or 2 points, then we can control really well what happens. Because for those targets, we have better ways of controlling the electric field. But if you have a target that has many, many nodes, then depending on the location and the local geometry of the head in that target, you may end up with targets that favor more this type of approach for inducing sham as compared to other targets.
One of the points you made is that it's very important to preserve the same montage between the active and sham condition. That's for the benefit of the subject, but also of the operator. You want to do a double blinding, right? Is that? Exactly.
So if we came up with montages that employ different electrode distributions for the sham and the active montage, the operator, even though you wouldn't know if you was doing sham or active, you would know that there's a difference. And based on the reported sensations or even the performance of the subjects in a given task, you might make some inferences about what type of stimulation is being applied. And of course, that if the design type is such that the same subject is, depending on the stimulation session, is stimulated with both active and sham conditions, and we have some studies that have that design, then it would be, even the own subject would be able to start picking these differences.
Okay. What about personalization? Is it something that you may want to do as well in an active sham scenario, as opposed to a general montage, active sham montage for everybody?
Yes, like I said, we believe in neuroelectrics that the future for those parameters is personalization. I mean, the technique has evolved and the methods have evolved to such a degree that today we can create these head models in a matter of hours, whereas some years ago we needed weeks. And many studies now, they are becoming more aware of that, and they are incorporating a budget for acquiring appropriate MRIs for the segmentation process, and that will enable the creation of computational head models. The other approach of using a single head model, it will undoubtedly lead to more variability of the results, because you're like we've seen from the last presentation by Maria Chiara, that using.
And finally, just to
yeah.
Sorry, just to close, I think we need to be minding of the time now. What about tES? You talked about TDCS here. Would the method also apply in tES? Would be useful there as well, tES or tRNS?
Yes, this method will apply to every waveform that you can think of. So thanks to the negligible capacitive effects that we have in tES, there's no phase difference between the current and the electric field. So the electric field just follows the current without any phase delay.
Okay, thank you very much, Ricardo. If there are no other questions, let me just check one last time. Not here or in Twitter. Let's see if we have any Twitter questions. Doesn't look like it. Okay, so thank you again. Let's move on to our next presentation by Laura Dubril. She's going to be talking about EG biomarkers of TDCS neuromodulation of executive function in healthy and ADHD populations.
Yep, thank you, Julio. So let me go full screen. Okay, can you see it okay? Okay. So thank you everyone for staying until the last talk. In this talk, I'm going to present the results of a study in which we combine EEG and TDCS in order to find physiological biomarkers of executive functions in healthy and ADHD populations. So this is a nice example of how we can use the combination of EEG and TDCS to find some interesting insights into our research. So as you may know, executive functions is a term that is used sometimes to define the meta level of cognitive functions that are essential for successful adaptation to all kinds of environments, including social and professional environments. And throughout the history, there have been several models of executive functions, but here we can see one proposed by Daphner and Searle in 2008, in which they divide executive functions into first order and second order. So first order executive functions are the most basic ones, like working memory, inhibition, initiation, and monitoring. And second order executive functions are those more complex functions that are built upon the basic ones. So they may include planning, organization, resisting interference, set shifting, affect regulation, and context appropriate behavior. On the clinical side, there are a wide range of clinical populations with impaired executive functions. For example, traumatic brain injury, depression patients, bipolar disorder, schizophrenia, dementia, or ADHD. And anatomically, the prefrontal cortex is thought to be the central hub of executive function networks, including its subunits. So, which include the paralimbic cortex, which is more in charge of initiation and monitoring, and the heteromodal association cortex, which is more in charge of working memory and initiation. And this includes the dorsolateral prefrontal cortex, which is the area that we're going to focus in this study, and the temporal lobe and the inferior parietal cortex. Physiologically, EEG has a high temporal resolution, as you may know, and this offers a great opportunity to further understand the physiology of executive functions. And more specifically, ERPs, or event-related potentials, are specific patterns in the EEG signals that are time-locked to some specific events or stimuli that have been established as relevant signatures of executive function. So, For example, some of the ERPs that we are going to focus in this study are P200, which is this positive peak here, and this is related to selective attention, and 200, which is this negative peak here, and this is more related to attentional effort, and P300, which is more related to conflict control and response inhibition. So the goal of this study was twofold. First, we wanted to assess the effects of tES on executive functions, both in healthy populations and clinical populations like ADHD. And more specifically, we wanted to investigate the role of the DLPFC laterality in order to further understand whether the left or the right DLPFC plays a more significant role in executive functions. And second, we wanted to find physiological biomarkers of executive functions using EEG to further understand the mechanisms of action of tES and the impact of state-dependent dynamics of tES. So the study design consisted on 20 healthy controls and 20 ADHD patients. Each subject performed 3 sessions in which they received tES targeting the right DLPFC, the left DLPFC, and a third session with sham. And for each session, they performed 2 conditions. So before and after the stimulation, pre and post, they performed the flanker task, which is a cognitive task, while we measured EEG and recorded behavioral metrics such as reaction time and accuracy. And here you can see the modeling of the electric field that we used for these specific montages. So to target the left DLPFC, we introduced an anodal electrode through F3 and cathodal FP2. And for the right DLPFC, we used a nodal F4 and cathodal FP1. And the specific protocol for each session consisted, as I said, first of all, they performed the flanker task while we measured EEG from these positions and we recorded the behavioral metrics. And then they received 30 minutes of tES stimulation at 2 milliamps targeting the left or the right DLPFC or sham. And then they perform again the flanker task while we measured EEG and behavioral metrics. So we could compare pre and post behavioral and physiological metrics. So we used the star stim divide from Neuroelectrics to apply tES and to record EEG. And just to give you a little bit of an idea of what is the flanker task. So it is a cognitive task that measures attention and inhibitory control, in which subjects are presented with a certain stimulus, in this case an arrow, which is surrounded or flanked by distracting stimuli. And the goal of the subject is to press the right arrow keys, the right or the left arrow keys, depending on the direction of the central arrow and ignoring the distracting stimuli. So in this case, we have 2 types of trials. We have the incongruent trials in which the flanker arrows, the distracting arrows point to the opposite direction as the central target, and the congruent trials in which the flanker arrows point to the same direction as the central target. So of course, the incongruent trials are more difficult than the congruent ones because they require to ignore the distracting arrows in this case. Okay, so the results on the behavioral side, they indicate that tES targeting the left DLPFC leads to a significant improvement in reaction time, both for healthy controls and ADHDs, and both for incongruent trials, which are the most difficult ones. And this effect, so the improvement in the faster reaction time is significant after stimulating the left DLPFC, and this effect is significant compared to right DLPFC and compared to sham. So this improvement in the, just one second. Okay, so this improvement on the behavioral side was correlated with an increase in the amplitude of P300 and a decrease in the amplitude of N200. So these 2 ERPs here are associated usually with an improvement in response inhibition in the case of P300 and an improvement in the efficiency of attentional allocation in the case of N200. So we know, or we can conclude that the improvement on the behavioral side is correlated with an improvement in response inhibition and attentional allocation, the efficiency of attentional allocation. And again, these results were significant after stimulating the left DLPFC compared to right and sham, which led to no significant results. And another interesting result is that the largest increase or decrease in ERPs occurred mostly around the area of stimulation, both for left and right DLPFC. So the effects occurred mostly, they matched the laterality of a stimulation. Another thing that we investigated was the effects of a state dependency. So what we found is that those subjects with more impaired executive functions were the ones who had a greater improvement after stimulation. So this confirms the idea that tES leads to greater modulation of physiology and behavior in subjects with baseline physiological signatures that are indicative of less adaptive processing. So basically, tES effects depends on the state of the subject before stimulation. So just to summarize, we found that a nodal tES to the left DLPFC leads to faster reaction times in the flanker task, both in healthy controls and ADHDs. So this suggests that the left DLPFC has a more important role in executive functions in those tasks that involve conflict resolution and response inhibition. And this improvement on the behavioral side was correlated with changes in N200 and P300 amplitudes on a trial-by-trial basis. So this suggests that there was an improvement in attentional efficiency and response inhibition. And finally, we also found that the baseline physiology predicts cognitive and physiological effects of tES. So this speaks about the state-dependent nature of tES. And finally, of course, I would like to thank all my colleagues that helped me with this work, especially my PhD advisors, Joan, Julio, and David, and my colleagues, Ali, Craig, Federico, Peggy, Anna, and Patricia. Thank you so much, and I'm happy to answer any questions now.
Let's see, you seem to have a question in the Q&A here, if I can raise it up. So from C. Jill, have you considered the convenience of using another tES approach protocols such as tACS to compare effectiveness of task improvement?
Yeah, absolutely. That's a good question. So one thing that we could do is to try tACS to kind of, modulate specific frequencies in the brain, and that could lead to definitely better effects or different effects compared to tES. Another way that we could do to change or to try to improve the effects would be to, instead of stimulating while at resting state, we could also stimulate during the task and see if that actually leads to any change. Also, what we thought in this case, we are using a standard bipolar montage because we wanted to compare these effects with other previous studies that we did using this specific montage. But I think that one thing that we could do to improve this would be to do personalized montages, as my colleagues mentioned before, personalized montages for each specific subject in order to maximally stimulate the DLPFC, the left or the right DLPFC for each specific head model.
Thank you. Yeah, I guess head modeling could also be used even if you don't personalize to analyze the average electric field on target and draw conclusions about the correlation of that with the outcomes, right?
Absolutely, yeah.
Okay, any other questions? Let's see. This one is done. Okay, I don't see another one right now from the public. So did you find any significant effects in the response accuracy?
Right, yeah, I didn't mention this because we didn't find any significant effects, but the thing is that, so accuracy didn't improve, but it also didn't get worse. So that means that subjects basically were faster in replying, but this was not at the expense of worsening the accuracy. So they maintain accuracy response accuracy, and they were faster. So that's still a good point.
Do you think that this technique could be used to develop biomarkers for ADHD, for instance, in the future or something like that?
Yeah, absolutely. So the fact that we found that these specific ERPs were being modulated by tES shows their value to being used as specific physiological biomarkers for executive functions, specifically in ADHD.
Thank you very much. Let's see if there are any other questions from the public or any other panelists. Doesn't look like it. Okay. So thank you very much, Laura. I'm also very happy that this is going to be one of the works that is going to go into your thesis, which you're about to present.
Thank you, Julia.
So I'm very happy about that. So with this, we're going to close our session. So thank you very much for your attention. It's been a pleasure to be with you from different parts of the world, from Barcelona, Menorca, and Boston, basically. So I hope you enjoyed it and you learned something useful. Until next time then. Bye.